In this video, we'll introduce the notion of a Markov network. We've seen before that a conditional random field can be written in a slightly different form from what we've seen before, as essentially a product of some factors. And in the case of a linear chain conditional random field, where we have unary potentials which correspond to neural networks, then these factors would correspond to these terms here, where we have unary factors, so the factors that involve a single y, and pairwise factors, where this factor involves two adjacent labels, two y's. So these would be the unary factors, these would be the pairwise factors. A very useful visualization of a given conditional random field model is known as the Markov network. So it's a network where the nodes are the random variables in our model, and edges are constructed and are added into the network based on a very specific reason. So the way we construct a Markov network for a conditional random field, which we've written as a product of factors, is that first we would write all of the different, so we have a node for each of the random variable in our models. In our case, each of the labels, if we had a sequence of length 5, then we have y1, y2, y3, y4, y5, as well as a node in this case for each of the input vector x1, x2, x3, x4, and x5. So now, then we would add edges for between each random variable that shares a factor in the product of factor form for our conditional random field. For the linear chain conditional random field, then this means that we would have, and also for a context size of radius 1, context window of radius 1, then we'd have these diagonal edges between each label y and its input at its left. So then we'd have also an edge between each label and the input at the same position. So those are the vertical edges here. And similarly, we'd have edges, diagonal edges like this between each y and the label to its right. So those correspond to this factor here, the factor between yk and xk plus 1. So those were all the unary factors, and then for the pairwise factors, they would correspond to the horizontal edges here between each yk and its neighbor yk plus 1. So what's useful with the Markov network visualization is that we can very easily identify certain conditional dependencies between the random variables of our model. So for instance, the Markov network respects what's known as the local Markov property, meaning that in the Markov network, a random variable is going to be independent of all other random variables that are not its neighbors, given its neighbors. So for instance, if I'm considering this random variable, its neighbors in this graph would be this one, this one, this one, this one, and this one. Well, the local Markov property tells me that y3 is going to be independent of y1, x1, y5, and x5, given its Markov blanket, so its neighbors, y2, x2, x3, x4, and y4. Okay, so that can be useful if we want to determine in our model whether certain random variables are dependent on each other or are independent, given other variables that we might observe. So if for some reason I was observing, so in the conditional random field, we always observe x1, all of the inputs, so that's x1, x2, x3, x4, and x5. So I've used a double circle to identify those nodes that are observed. But imagine that I also happen to observe in the sequence y2 and y4, so maybe for some reason I actually have this information. Well, the local Markov property would tell me that the distribution over y3, given these 5 nodes, actually does not depend on y1. So I can just ignore it and compute the conditional which is only going to depend on these five nodes, and the probability will of course depend on the particular value of y3 for which I want to compute the probability. In fact, we can say something even a bit more general, which is if I have two nodes, well then there are going to be conditionally independent if all the paths between the two nodes contain at least one of the conditioning nodes. So one of the node that I might be observing and I'm conditioning over. So for instance, if I'm wondering, so imagine in the conditional random field, again, when we use it, we always observe all the input. Now imagine that I'm also observing y3, and I want to know whether y1 depends on y5. In this case, there's one path between y1 and y5. So it's this path. Actually, there are other paths. I could go like this. So there's more than one path. I could go like this and like that and so on. Well, it turns out in this case, we can easily see that each path between y1 and y5 actually contains one of the node I'm conditioning on. That is, it either contains one of the inputs. So each path that goes through an x node would be blocked by the x node that's observed, that I'm conditioning on. And if I'm assuming I'm also observing this, well then any node that stays up like this and goes through y3 is going to contain a conditioning node. So it's going to be blocked in a sense. And so for that reason, we could say that y1 and y5 is independent, conditionally independent, given x1 up to x5 and y3. So that's a useful property of the Markov network. It allows us to identify a lot of conditional independencies very easily. Another thing that's important to understand about conditional random fields is that they're known as undirected graphical models, to be distinguished from directed graphical models like hidden Markov networks and Bayesian networks in general. And so what this means is that when I write it in the form of a product of factors, well, all of the factors, so I'm giving an example here where we have conditional random field with with no context window, or context window of size 1 that only contains the input at the current position. So in this case, I can think of this as only containing two types of factors. Well, in this case, in a conditional random field, these factors only need to be non-negative. So they need to be greater or equal to 0. That's the only requirement that I have in an undirected graphical model, is that when I write it as a product of factors, well, the factors themselves, they only need to be such that they are always greater or equal than 0. So that's to be contrasted with a hidden Markov model. So if we visualize it as a Bayesian network, that is a network where the nodes are the random variables and the edges are now directed, well, each edge in this case corresponds to a conditional probability in the model. That's a property of a Bayesian network. In this case, for a hidden Markov model, this arrow here would correspond to the conditional, would illustrate that would correspond to the conditional probability of y2 given y1, and also x2. The arrow from y2 to x2 would correspond to the conditional probability of x2 given y2. So the arrows, they are saying essentially is that in the generative story behind the model, y2 was generated based on y1 only, and then x2 was generated based on y2 only. So because now, if we write it in factor form, then all the factors will correspond to these probability distributions. And it means that we do satisfy the fact that these, because they're probability distributions, they're going to be greater or equal than 0. However, in a directed graphical model, the factors also need to sum to 1 with respect to one of the arguments here. So for instance, this factor would sum to 1 with respect to xk. because it's a conditional probability. It's a distribution over xk. And similarly, this factor between pairs of labels would sum to 1 with respect to yk plus 1 because it's a conditional distribution over yk plus 1. Okay, so that's an important distinction between a directed graphical model like an HMM and a conditional random field, which is an undirected graphical model. So now the edges do not correspond to conditional distributions. They just correspond to factors, or they're associated to with factors or compatibility function, which just express a preference for the values that can take each of the random variable in the factor or compatibility function. And in particular, if we were to try to identify conditional independences in the directed graphical model, and so from the Bayesian network, it would actually be more complicated. So there's the deseparation rule, which I won't explain here, but you can find in most textbook in on graphical models, which requires a bit more complicated rule than just looking at the paths between the variables and identifying whether on each path between the random variables there is at least one node which corresponds to a conditional node. There's a slightly more complicated rule due to the fact that the edges between the nodes are directed and correspond to normalized factors, to conditional distributions. All right, so that covers Markov networks and as well as the distinction between undirected and directed graphical models.